All right, welcome back. Today's lesson is on 5.6.1, something called related rates. Before we talk about related rates, we're going to do a quick review of implicit differentiation because related rates is going to use the same concept. All right, so we're looking to find dy dx, so we take the derivative. Derivative of x cubed is 3x squared, plus derivative of y cubed is 3y squared, multiplied times the derivative of the inside because of the chain rule. Derivative of y is dy dx. Now you might recall when we did implicit differentiation, we talked about how I could technically write a dx here. Because using the same idea of chain rule, derivative of x cubed is 3x squared times the derivative of the inside. Well, the derivative of x can be dx when we're taking the derivative of x with respect to x. But we don't need to because dx is just 1, right? And then, we got to finish this up. Derivative of 27, 27 is a constant. That's 0. Essentially, we've done the derivative now. All that's left is to get dy dx by itself, if you care to. In this case, if we got dy dx by itself, it would be negative 3x squared over 3y squared, which is the same thing as negative x squared over y squared. All right. Here's where we talk about related rates. Many real applications we encounter have to do with change over time, right? It's how fast things are changing over time, and we can differentiate with respect to time instead of with respect to x or with respect to y or any other variable. We can use this idea of implicit differentiation to take a derivative with respect to time. So if we want to know how fast x and y are changing over time, we can take the derivative with respect to time, and we can find dx dt and dy dt. What are dx dt and dy dt? They're rates. They're how fast x and y are changing over time. If this seems confusing, don't worry. We're going to do a couple examples to try to help clear this up. All right, just straight up first, how to take the derivative with respect to time. Same idea as implicit differentiation. Here's the same equation as before, but this time I'm going to take the derivative with respect to time. So with respect to a new variable t. So same thing here, derivative of x cubed is 3x squared. Because of the chain rule, I'm going to then multiply times it by the derivative of the inside. But the derivative of x with respect to time isn't dx dx, it's dx dt. Plus, derivative of y cubed is 3y squared. Because of the chain rule, we then multiply times the derivative of the inside. The derivative of y with respect to t is dy dt. Equals derivative of 27. 27 is a constant. That derivative is still 0. You'll notice it's a very similar problem, but this time I have a dx dt and a dy dt in my equation. What are dx dt and dy dt? They're rates of change with over time. They're how fast x is changing and how fast y is changing. All right, I think we're ready for an actual example. We're going to ease into this. We're going to do this example, but it's going to be 3 different questions on the same problem. All right, so first question. It says Phoebe is traveling east on Alamo Street at 40 feet per second. So that's how fast Phoebe is traveling. And Calvin is traveling south on Height Street at 30 feet per second. So that's how fast Calvin is traveling. Yes, I missed the H in south. Sorry, I'll go back and fix it later. All right, here's our question. Let x be Phoebe's distance from the intersection and y be Calvin's distance. So those are already marked for you. Write each rate below. Explain why dy dt is negative. All right, so dx dt. That's how fast x is changing with respect to time. How quickly is x changing? Well, it's changing at 40 feet per second. Dy dt is how fast y is changing over time. Well, how fast is y changing? Y is changing at 30 feet per second. But I'm actually going to have a negative 30 here. Why negative 30 feet per second? Because this distance y is getting smaller. It's not getting bigger. Since Calvin's traveling south, that rate is getting, that y value is getting smaller and smaller and smaller, right? That distance is shrinking. So I have a rate that's negative so that my distance will shrink and become smaller and smaller. So this rate is negative because y is shrinking in size. Just like this one's positive because x is growing. All right, next question. Same problem, different question. Now the question is saying use your knowledge of right triangles to write an equation that relates x, y, and z, then differentiate your equation with respect to time. All right, so I've got a right triangle here. I've got three variables, x, y, and z. How are those related in a right triangle? They're related by the Pythagorean theorem. X squared plus y squared equals z squared. Now we're going to take that equation and we're going to differentiate it with respect to time, with respect to the variable t. So the derivative of x squared, well, that'll be 2x, times the derivative of the inside, so times dx dt, since my variable is t for time, plus variable of the derivative of y squared would be 2y, multiplied by the derivative of y, so times dy dt, equals derivative of z squared, you guessed it, that's 2z, times the derivative of the inside, derivative of z with respect to time is dz dt. I can leave my answer like that. If I wanted to, I could divide all of those by 2 and simplify my equation a bit. I think I'm going to do that. I'm going to rewrite this as x times dx dt plus y times dy dt equals z times dz dt. All right, we just took that equation, x squared plus y squared equals z squared, and we took the derivative with respect to time. This may seem weird, like why are we doing that? Why do we care? The last problem is going to indicate why we care and why this thing is super useful. All right, same problem, but this time I'm given a little bit more information. Phoebe is 200 feet from the intersection, so I know this is 200. Calvin is 600 feet from the intersection, so that distance is 600. Is the straight line distance between them increasing or decreasing, and at what rate? So the question is, if Calvin's going south and Phoebe's going east, this distance between them is going to be changing. The question is, at this moment in time, is that distance shrinking or is that distance growing? Well, we just wrote an equation that was an equation that showed the relation between the rates of x, y, and z right here. So we're going to use that equation and plug in the things we know. So I've got x times dx dt plus y times dy dt equals z times dz dt. Now at this moment in time, we know a number of these values. We know x. X is 200. So instead of writing x, we can put in a 200. We know dx dt. Dx dt is how fast x is changing. We already answered that in the first part. X is changing at 40 feet per second. Plus, we know y. Y is 600 feet. Times, we also know dy dt. Dy dt is 30 feet per second, but negative, remember, because y is shrinking. So negative 30. I think I'm going to make these color codes match. All right. The question is, do we know z? It doesn't say it there, but we can certainly figure it out because we know x squared plus y squared equals c squared. We already wrote, we know x squared plus y squared equals z squared. So even though it didn't give us z, we can certainly figure it out. Since x is 200, 200 squared, y is 600. 600 squared, that should be z squared. So we'll just do this work off to the side. I'll use my calculator with that. I get z is approximately 632.4555 feet. All right, so we can do that. This will be equal to 632.455 times dz dt is the one thing I don't know in this equation. But that's okay, because that is what I'm trying to find out. I'm trying to find out if that distance between them is increasing or decreasing. In other words, I'm trying to find the rate at which z is changing. In calculus, what's the expression for the rate at which z is changing? It's dz dt. So I'm trying to figure out that. I've got an equation here. Here's everything filled in. The only thing I'm missing is, dz dt. So, solve. I get negative 15.811 is equal to dz dt. So, since that's a negative, is z increasing or decreasing? Well, z is decreasing, so that distance is actually getting shorter right now. And at what rate is it decreasing at? It's decreasing at negative 15.8 feet per second. Related rates helps us to find how fast things are changing. All right, we're going to do one more example. The example we're going to do is going to be similar to the one you're going to see in your homework. The one in your homework is going to have a question that just asks you to do some calculus to write an equation, and then there's going to be a second part to it where it asks you to use that formula, use that equation to solve something. So this one says the volume, width, and height of a box with a square base are related by the equation volume equals width squared times height. We're being asked to write an equation that relates dv dt, how fast the volume is changing, to dw dt and dh dt. All right, well, I know volume equals w squared times height, so I want to find the derivative of this with respect to time. Derivative of v is dv dt. Derivative of this side, be careful, that's a product. It's going to require the product rule. Product rule says you take the first times the derivative of the second. First is w squared times the derivative of h would be dh dt plus second times the derivative of the first. Second is h. The derivative of w squared would be 2w times dw dt. I like putting my 2 in front, but for showing my work, I'll go ahead and write it like this. 2w times dw dt. And I'll go ahead and leave my answer like that. That's fine. Normally, I'd prefer to write the 2 out front, but that's fine. There's dv dt. There's an equation that relates dv dt to dw dt and dh dt. Done. The next part of this question says, suppose the width of a square-based box was increasing by 2 centimeters per second, and the height was increasing by 3 centimeters per second. How fast is the volume of the box changing when the width is 8 and the height is 12? I should have said changing. I wrote increasing. Oh, well, I suppose since the width and the height are both increasing, then the volume is going to get increased. It's definitely not going to get smaller, so that's fine. But I'm trying to find how quickly the volume is changing. All right, well, let's look at my equation. There's an equation that gives me how fast volume is changing when I've got a square box. So let's use that equation. All right, dv dt, I don't know because that's a change in volume, and that's what I'm being asked. I'm being asked how fast is the volume increasing, how fast is the volume changing, so I definitely don't know that one. That's what it's asking for. Let's see if I know the rest of them. W stands for width. Width is 8 centimeters. So 8 squared. dH dt is how fast the height is changing. Well, the height is changing by 3 centimeters per second. Plus height. Well, the height is 12. Times 2w. Well, w is the width. We already said the width. Width was 8. Times dw dt. Well, dw dt was how fast w is changing. Let's see. Yep, here it is, right there. The width was changing by 2 centimeters per second, right? Width was increasing by 2 centimeters per second. So dw dt is 2. Calculate all that out. I'm going to use a calculator for that one. I get 576. Now that 576 isn't just sitting there, that's how fast the volume is changing over time. In this case, the volume is being measured in cubic centimeters. I can tell that because all my measurements were in centimeters, and everything was changing per second, so cubic centimeters per second. Cubic centimeters per second. By the way, that cubic centimeters per second label bears itself out in the math. This problem here, I could have put my labels in, and you would see that the labels end up justifying that cubic centimeters per second. I'll show you really quick here just to prove it. So if you're ever not sure, you can put the labels in and it will work out. So let's see here. All right. So if instead of just putting in 8 was again 8 centimeters. So if I did 8 centimeters squared, and 3 was a rate, that was dH dt, that was 3 centimeters per second. So 3 centimeters per second. Well, if I square this one, that'd be 64 centimeters squared times 3 centimeters per second. Centimeters squared times another centimeter, that's centimeters cubed. 64 times 3, that's 192. It's 192 centimeters cubed per second. Same label. Now I didn't do this part of it, but I certainly could. I'd still get a centimeters cubed per second, and when I added them together, that's how I got this 576. But if you're not sure of the units you should add to it, just plug those labels in. The math works out just fine. All right, we're definitely going to talk about this in our class live, but I want to end this video now so we have plenty of time to talk. Your assignment when we get there is 5.6.1. As always, I'm at my office hour if you need me.